So now we get to titration, and this has direct application to what we're doing in lab right now. So, review, an acid-base titration, we take a solution of a known concentration, we react that with a solution of an unknown concentration. One of those is an acid, the other is a base. We monitor the pH either with an indicator or with a pH meter. And at the equivalence point, we know that the number of moles of acid is equal to the moles of base. Stoichiometry tells us the ratio there, and the titration is complete. From that information, we can calculate the concentration of the unknown solution. Illustration. Here we've got an acid, and we're using a base to titrate it, and so we're adding base to the acid, and they neutralize each other, and so this becomes less and less acidic until we add just a smidge too much sodium hydroxide, well, hydroxide, and we get to technically the end point where our indicator has changed color. So it was clear, it was getting a little pink, but when we swirled it, it goes away, and then we get to the point where just even a fraction of a drop changes it from colorless to pink. And that's our closest estimation of the equivalence point. So we can also graph the information. We call these titration curves or pH curves, where we plot the pH of the solution versus the volume of the known solution that's been added. So here's pH on the y-axis and volume of sodium hydroxide added. This is for the titration of a strong acid with a strong base. So here we're taking 50 milliliters of 0.1 molar HCl. We're titrating it with 0.1 molar sodium hydroxide. And we end up with our equivalence point at 50 milliliters because it's a one-to-one stoichiometry. The concentrations are the same, and so we'd need equal volumes of each. The equivalence point is the inflection point, or the point of inflection in this graph. That's where the slope changes. So here the slope is becoming more and more positive, and now it's becoming more positive, and now it's becoming less positive. So there's that point of inflection. Very close to the equivalence point, we see that the pH changes rapidly. At the beginning, it changes very little. At the end, it changes very little, but near the equivalence point, it changes dramatically. And that's why when you're adding one drop, it can just change like that, because one drop is a lot at the equivalence point. Now, the shape of the actual curve depends on the strength of the acid and the base, concentrations, things like that. So let's look at how you would calculate the pHs for these things. The first titration we're going to look at is a strong acid with a strong base, because that's a little simpler than when you do weak acids. So the 25 milliliters of 0.1 molar HCl, titrating it with 0.1 molar sodium hydroxide. First thing we're going to do is calculate the volume of sodium hydroxide needed to reach the equivalence point. Well, at the equivalence point, we need equal moles, considering the stoichiometry, of hydrogen ion and hydroxide ion. So what we've got here, we've got 25 milliliters. Or 0.0250 liters. So 0.00250 moles of HCl. 25 milliliters of 0.1 molar. At the equivalence point, how many moles of sodium hydroxide should we have? Well, this is moles of HCl, and we need 1 mole of sodium hydroxide per every 1 mole of HCl. So we need 0.00250 moles of sodium hydroxide. Okay. What volume of 0.1 molar sodium hydroxide is going to give us that? Well, we could calculate it, right? 0.00250 moles, and the concentration is 0.1 moles per liter. And so that's going to give us 0.0250 liters, or 25 milliliters. You guys are really quiet right now. I'm not sure what it means. It seems like it should mean something.
Monday.
It does feel like Monday, but it is Tuesday. It is Tuesday. Yes, I understand. Okay. Yeah, you are operating like it's Monday. You guys are all in a daze. So we figured out what volume of sodium hydroxide will get us to the equivalence point. What is the initial pH of this solution? Well, this is a strong acid, right? HCl. So that ionizes completely. So the concentration of hydrogen ions is going to be equal to the acid concentration, right? So that means that the hydrogen ion concentration is 0.110 moles per liter. So then the pH is what? pH is 1. So here on our graph, we've got 1 red dot. At 0 volume added, our pH is 1. Okay, so what's going to happen after we add 5 milliliters of sodium hydroxide? Well, 5 milliliters of sodium hydroxide is how many moles? 0.0050 liters times 0.1. So it's going to give us 0.000500 moles of sodium hydroxide. We started with 0.0025 moles of hydronium ion. We're adding this many moles of hydroxide ion. So that's going to react with an equal number of moles of hydronium ion, and so we're going to end up with 0.00200 moles of hydronium ion. We can't just plug 0.002 into the pH equation. We need the concentration. The volume of the solution has changed because we added 5 milliliters to it. So our initial volume was 25 milliliters. We added 5 milliliters. So we have to use our new volume when we calculate the concentration of hydronium ion. And then you get the pH would be the negative log of 0.0667. So the pH (1.1758), 1.176. Any questions? And then we're going to keep adding. Add 10 milliliters, add 15 milliliters, add 20 milliliters. These calculations are going to be similar for that to the 5 milliliter one. Let's just do one of them. Pick one, 10, 15, or 20. 15. That's a good choice. It's right in the middle, right? So 15 milliliters. So that's 0.0150 liters times the 0.1 moles per liter for the sodium hydroxide. So there's our moles of sodium hydroxide. So we've got hydroxide ion plus hydrogen ion. They're neutralizing each other and making water. So before we added anything, we had 0.0025 moles of hydrogen ion, and none of this. And now we're adding 0.00150 moles. And so then we're going to end up with none of this and 0.00100 moles of the hydrogen ion. I started with this many moles of hydrogen ion. I added this many moles of hydroxide. They're going to neutralize each other. So I'm going to subtract this from my starting concentration, and that's how I'm starting number of moles, and that's how I end up with my final number of moles of hydrogen ion. So then we've got moles of hydrogen ion. We need molarity, so we need to divide by the volume. Well, the volume is the initial volume, which is 0.250 liters, plus the 0.0150 liters that we added. So I'm getting a concentration of 0.025. And pH is the negative log of that, 1.6020. So that's this point right here. So we can be thankful that in our lab today we don't have to calculate the pH of every little point. We're going to use a pH meter and measure the pH. That's something to be happy about, right? One of the ways I get through life is in any situation, no matter how horrible, you can always imagine something that would be worse. I will not make you calculate a gazillion of them on the test. Would I make you do one problem like this? Sure. Yeah. Okay, so what's the pH? Yeah, question?
This is upcoming test, right? Upcoming test is 15 and 16.
The upcoming test is 15 and 16. This is 17. So this is on the next one. There's something else to be thankful for, right? Okay, let's figure out what the pH is at the equivalence point. So we've got hydroxide ion, we've got hydrogen ion, and those are making water. We have now added equal amounts of the acid and the base in terms of moles. So do I have 0 for these? Well, they're approximately 0. So this ends up being a neutral solution, right? Equal amounts of hydroxide and hydronium ion. So what's the pH? 7. Because the Ka for water is 1.0 times 10 to the minus 14, right? Which is equal to the hydronium or hydrogen ion concentration times the hydroxide ion concentration. So the hydrogen ion concentration then is 1.0 times 10 to the minus 7, so the pH is 7. Yeah?
So I know that that value changes depending on the temperature, but are we going to be required to remember that constant, or does it not matter since it varies?
This constant, 1 times 10 to the minus 14th, you remember that.
Okay.
Yeah. And I don't think that changes significantly with temperature.
Would we have to, oh, okay. So we wouldn't have to calculate a different constant depending on the temperature?
I don't think so, no.
Okay.
But you should definitely know that Kw is 10 to the minus 14. Okay, so we've got our pH at the equivalence point. Now we got 30 milliliters of sodium hydroxide. So before we had approximately 0. It's actually 10 to the minus 7, but that's so small compared to these other things that we say it's essentially 0. Starting with the 0.0025, now we've added 0.00300 moles of the hydroxide. So that's going to react with all of the hydronium ion, and it's going to leave us with an excess of 0.0050 moles of hydroxide. So we have to calculate the concentration. We'll calculate the concentration of the hydroxide ion. So 0.00050. My phone is just buzzing in my pocket. It's children and students, and oh my goodness. So there's the volume added, and here's our initial volume. So 0.0005 divided by 0.03 plus 0.025. So 0.009090, repeating. That's the hydroxide ion concentration. We need to find the pH. You can't really do pH directly from hydroxide ion concentration. So this is where the circle of pH comes in. You're on opposite sides. You got to go around one way or the other. Personally, I like going through the pH side because then we've got the POH side to the pH, because then you can just use the 14 minus. So I'm going to find out what the POH of this is. So I take that concentration I just calculated, take the pH negative log of that. So I've got 2.04, and the pH will equal 14 minus that. .96. Any questions? What if we keep going? Well, it's going to be a very similar calculation. Let's do 50 milliliters. Well, let's be consistent. We're doing it that way. So we started out with 0.00250 moles of that. Now if we're adding 50 milliliters, 50 milliliters is 0.0500 liters, and it's 0.1 molar. So this is going to be 0.00500 moles. So So we've got 0.00500 moles of the hydroxide. So that's going to use up all of the hydrogen ion. So that's going to be essentially 0. And 0.0025 of this is going to be used up, so we're going to end up with 0.00250 moles. Of hydroxide. You okay with that? It's subtracting. We have to change this into a concentration. We've got the 25 milliliters and 50 milliliters. So now I get a whole bunch of 3s. So I can calculate the pOH of that. 1.477. Yeah. So then pH equals 14 minus that, 12.52. Yes, nailed it. There it is, 12.52. Any questions? Calculating all those points is tedious. And the most difficult thing about it is just to remember what you were trying to do in the first place. Any questions? So this is the overall pH curve for strong acid and strong base. So adding sodium hydroxide, the pH goes up. Before the equivalence point, we have an excess of hydronium ion. After the equivalence point, we have an excess of hydroxide ion. And the equivalence point for strong acid, strong base is always going to be at pH 7. If you're titrating a base with an acid, just basically doing the opposite, the curve has a very similar shape. It's just backwards. Right? Now we're starting at high pH with an excess of hydroxide. The equivalence point is still going to end up at 7. And then afterwards, we have an excess of hydronium ion. Okay. So here is a typical kind of problem. A 50 milliliter sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. So we've got sodium hydroxide and nitric acid. And those are going to neutralize each other, right? And make water and sodium nitrate. Do we care about the sodium nitrate? No, we don't. Just debating which way to go with this. So I'll try to keep a similar format to what we've done following the patterns in the book. So we've got 50 milliliters of 0.2 molar sodium hydroxide. I'm going to do this one with millimoles, just to show you that it makes all the math much nicer. So I've got 50 milliliters of that sodium hydroxide, and the concentration is 0.200 moles per liter. And what I've been doing is I've been converting milliliters to liters, right? And then we end up converting back sometimes. 0.200 moles per liter is the same as 0.200 millimoles per milliliter. I'm multiplying the numerator and the denominator by 10 to the minus 3. It's still the same, right?
Preference which one we do on the test?
I do not have a preference for which one you do on the test. Do whichever one seems easiest to you. So if I multiply these, then I get 10.0 millimoles. If I did it the other way, I'd end up with, what, 0.010 moles. So I've got 10 millimoles of sodium hydroxide. And I'm starting out with no nitric acid. And then I'm adding 60 milliliters of 0.2 molar nitric acid. So 60 milliliters times 0.2 molar, this is going to give me 12 millimoles of the acid. So you've got more acid. We've gone past the equivalence point. But we're trying to find out what the pH of this mixture is. So we've got 12 millimoles of acid, 10 millimoles of sodium hydroxide. So what's going to be left? We're going to have 2 millimoles of the acid left and none of the hydroxide, essentially none. So I've got 2 millimoles. Well, actually, it's only 1 0. 2 millimoles of the nitric acid. It's a strong acid. And then I need to divide by the total volume, which is 50 milliliters plus 60 milliliters. I've got millimoles divided by milliliters. We've got 2 divided by 50 plus 60. 0.01818, repeating, molar. So the pH is the negative log of that. .74. Pardon me?
That changed it a lot.
Yeah, it did change it a lot.
2 millimoles changed it by.
Mm-hmm. Well, the 2 millimoles seems like a small amount of acid, but it's in 110 milliliters. And so, you know, if it was in 5 liters, it wouldn't change the pH nearly as much.
How much is that amount in milliliters, 2 millimoles?
Well, it depends on the concentration. So 2 millimoles of this 0.2 molar nitric acid would be, I think, 10 milliliters?
Oh, that's actually a lot. I feel like if we were doing this experiment, you'd probably realize that you made a mistake.
Yeah, if you went that far, you'd realize you made a mistake. Any questions? So, strong acid, strong base titration, you look at the moles of acid, the moles of base, you look at the relationship, because here it's 1 to 1. Sometimes it might be 2 to 1, or 1 to 3 or something. You can't ignore that. You're going to look at how much of these reacts and what's left. Only one of them should be left. And then you have to find the pH based on that, and you have to take into account the altered volume. Okay. Okay, so let's look at a weak acid with a strong base. So same concentrations here, same amount to start with. So sodium hydroxide and this formic acid, how much sodium hydroxide do we need to reach the equivalence point? I hear little mumblings, but I can't understand any of them. Somebody be brave. It'd be the same amount, 25. So the volume at the equivalence point doesn't depend on whether it's a weak acid or a strong acid. It's just the number of moles. Because at the equivalence point, you've got equal moles. They neutralize each other. Doesn't matter if it's strong or weak. So this one's 0.1 molar, the base is 0.1 molar, then we need an equal volume to the volume of the acid, and so 25 milliliters, just like the previous calculation. Now it does get different for the rest of this. So let's look at the initial pH. So formic acid, the Ka is 1.8 times 10 to the minus 4. So we look at the initial concentration, or the concentration of the acid is 0.1 molar, and that's going to dissociate partially, right? So we're going to lose X of that and gain X of each of these. And so we get our ice table set up here, and at equilibrium, these are the concentrations in terms of X. And this is what we were doing a lot of in chapter 16. Sorry, I accidentally switched the slide. That's better. So our Ka is 1.8 times 10 to the minus 4. And so that's going to equal the products, X times X, divided by the reactant, 0.100 minus X. And for most of these calculations, we can use the X is small approximation. So that gives us that X, which is the hydrogen ion concentration, is going to be equal to the square root of 0.100 times the Ka. So I'm getting 0.0042426. You can really only say 2.6 there. So then we find the pH based on that. 2.37. Any questions? Add 5 milliliters of the sodium hydroxide. So now we need to do one of these before and after tables. So we started with 0.00250 moles of our acid. We added 0.000500 moles of hydroxide. That's going to react with the acid. So that's going to reduce this number of moles to 0.0020 moles. And now we're going to have a number of moles of our conjugate base. We didn't have this with the strong acid and strong base because the conjugate base doesn't have any pH action. It's neutral. But now we've got this. So we have moles of the acid, we have moles of the conjugate base. This is now a buffer solution. And we determined earlier that X is small seems to be working here, so we can use the Henderson-Hasselbalch equation. So we can say that I keep forgetting to choose a marker and switching the slide instead. pKa plus. Now, do I have to figure out what the new volume is and divide each of these by the volume? I did in the other one. Well, the base is going to be moles of hydroxide per liter of solution. And the acid is going to be moles of acid. I'm sorry, it's not hydroxide. It's moles of A minus. And this is going to be moles of HA divided by liters of solution. Is the volume of the solution the same for both of those? Yeah, because they're in the same beaker, right? So the volume of solution cancels out using the Henderson-Hasselbalch equation, and so we don't have to worry about it. So I need pKa, so the negative log of 1.8 times 10 to the minus 4. So 3.74 plus the log of 0.000500 divided by 0.00200. Using millimoles gets rid of a lot of these zeros, which is kind of nice. .14. So that's using the Henderson-Hasselbalch equation. The other way you could do that is you can take this moles of your acid, moles of the conjugate base, divide by the volumes to get the concentrations, set up an ice table, and solve it that way. You should end up with exactly the same answer. Well, what about adding more? So we are still before the equivalence point. We determined first slide that it was 25 milliliters was going to be our equivalence point. So up until the equivalence point, we have acid and conjugate base present, and so it's a buffer all the way. Let's do the 12.5. So we're gonna do the calculation for this one. So at 12.5 milliliters of hydroxide added, we've added 0.00125 moles of the hydroxide, and so that's going to use up half of the original acid, and it's going to create an equal number of moles of the conjugate base. So what we're showing in this table is the results of before and after tables. So pH 3.7447 plus, look at the moles of the base, divided by moles of the acid. Oh, those are equal. This is the half equivalence point. We've added, we're halfway to the equivalence point. At that point, you have equal concentrations of acid and conjugate base, and so the pH is equal to the pKa. Any questions? What about at the equivalence point? So before and after table. So before, no hydroxide, there's our starting number of moles of the acid. Now we're adding 0.00250 moles of hydroxide. That's going to completely react with our acid, and so we're going to have none of the acid, and we're going to have 0.00250 moles of this conjugate base. This isn't a buffer anymore. We have the conjugate base. Is that just going to sit there as the conjugate base? No, some of it's going to act as base and reform some of the weak acid, right? So we do have to do an equilibrium calculation here. So we've got CHO2 minus, and that's going to react with H2O to form HCHO2, the acid, plus hydroxide ion. So we're starting with, now this is an ice table, so we should be using concentrations here. Yeah, let's just use concentrations. So what's our volume? Our volume is 50 milliliters. So I've got 0.00250 moles in 0.0500 liters. So 0.0500 molar. So we're going to start that with initial, and then we've got change and equilibrium. So we're starting with none of that and essentially none of this. So then we've got minus x and plus x and plus x. And so at equilibrium, now I'm out of space. Can I use Ka here? No, because this is the weak base, right? So I need to use Kb. Remember, Kb equals Kw over Ka. So 10 to the minus 14 divided by 1.8 times 10 to the minus 4. So 5.55 repeating times 10 to the minus 11. That's my Kb. That's going to equal x squared over 0.0500 minus x. Given how small this is, I'm sure that x is going to be small. And so we can use the x is small approximation. This is going to end up being the square root of 0.0500 times our very small Kb. I don't know why I can't keep that number in my head. It's minus 6, right? So I found out what x is. So I've been doing all this lovely calculating and wait, what was I trying to figure out? pH. So I found x. What does x represent? It represents a hydroxide ion concentration. So I'm going to find the pOH using that negative log of that 5.778, and then I'm going to subtract that from 14 and get 8.22. Looks about right. Any questions? So the equivalence point when we're titrating a weak acid is always going to be basic. Because after we've neutralized all of the acid, we have that weak base present, and it will react to a slight extent with water and form a slight excess of hydroxide ions. So the solution will be basic at the equivalence point. After the equivalence point. So, wait. So this is all the work I just did. Whatever. Okay. pH after the equivalence point. So 30 milliliters. So we had 30 milliliters of the hydroxide. That gives us 0.003 moles of the hydroxide. That's going to react with all of the acid and leave some extra hydroxide. So now we have some hydroxide ion, some strong base, and we have this weak base present. The strong base wins. It completely overwhelms the weak base, so we don't even have to think about the weak base. So all we need to do is look at the number of moles of hydroxide ion, convert that to molarity. So we do have to consider volume of solution. So that's moles of hydroxide ion. And volume of solution is going to be 0.0250 plus 0.030 liters. .009090, that guy again. That's the hydroxide ion concentration. So we can calculate POH, 2.04, and the pH is 14 minus that. 11.96. Any questions? Isn't this fun? Anybody who thinks it's fun is not willing to admit it. It's okay. As we keep going, we're going to do the same type of calculation. We've got excess sodium hydroxide. So we figure out how many moles of hydroxide was added. We subtract the moles of acid initially present, and we just look at the moles of hydroxide that are present. We have to convert that to molarity using the new volume. And so the volume keeps changing. So now here at, when we've added 50 milliliters, our total volume is 75 milliliters. And let's just do this real quick with millimoles. So I had 25 milliliters of my acid times 0.100 molar. And so that's 2.50 millimoles of the acid. And I've got 50 milliliters of 0.1 molar sodium hydroxide. So that's 5.00 millimoles of hydroxide. So this is going to react with the acid. It's going to use up all the acid. So it's going to use up 2.55 millimoles of the hydroxide and leave me with 2.500 millimoles of hydroxide. So I've got 2.5 millimoles of hydroxide ion, and I want to divide by the total volume, 50 plus 25, 75 milliliters. So I got 2.5 divided by 75. So that's my hydroxide ion concentration. And then POH. .477. So pH equals 12.52. I find these numbers easier to deal with because they're more of a reasonable size. The other ones, you've got like 0.001. It's like, well, it's not really far enough to go to scientific notation, but then you've got some others that are, and then it just gets all ugly. I like millimoles. So here's our overall pH curve. So initial pH, we're calculating that from the Ka of the weak acid, taking into account the concentration, so we do an equilibrium calibration here. Here we have the buffer range, and so in this region, once we've added some base, but before we get to the equivalence point, you can use the Henderson-Hasselbalch equation. At the equivalence point, we're looking at a weak conjugate base, and so you got to use Kb and figure out the pH from that. After the equivalence point, now we have hydroxide ion in excess. And so you figure the molarity of the hydroxide and get to the pH from there. Okay. A 40 milliliter sample of 0.1 molar nitrous acid is titrated with 0.2 molar KOH. Calculate the pH at the equivalence point. Okay, so, well, let's write an equation. So we're going to make some water and some salt. So I've got 40 milliliters of 0.1 molar acid. So that's going to be 4.00 millimoles of the acid. I've titrated it with 0.200 molar KOH. So if I have 4 millimoles of acid, how many millimoles of KOH are added at the equivalence point? How many millimoles of acid? You guys are having a brain fart. Okay, so here's my acid. And what's the ratio of KOH to HNO2? One to one. It actually doesn't matter. At the equivalence point, the moles of acid are equal to the moles of base. The moles of hydroxide equals the moles of hydrogen. Now, is this an equal volume? Is it 40 milliliters? No, because the concentrations here aren't the same. But the number of millimoles of hydroxide is. So 4 millimoles. So then what I'm trying to figure out here is the pH of this solution, right? So I need to know the volume and I need to know what's in here. So I've got 4 millimoles of KOH. Well, how many liters or milliliters of the KOH solution did I add? Well, I can use the number of millimoles to calculate that. So I've added 20 milliliters of that solution. You guys okay with that? So I've got 20 milliliters of that. I've got 40 milliliters of the HNO2. So the 4 millimoles, 4 millimoles, and I've added 4 millimoles of KOH. So those use each other up, right? They neutralize each other, so I've got 0 of those. We don't care about the water. And I've got 4 millimoles of this KNO2. This nitrite ion is the conjugate base of a weak acid. So we have to look at Kb for this thing. We've got NO2 minus plus water So let's switch back to concentrations now. I've got 4 millimoles of that. And the concentration depends on the total volume. The total volume is 40 plus 20, 60 milliliters. So 4 divided by 60. 0.06666. So in my ice table, 0.0666 molar and 0 of these other things. And then minus x plus x plus x. Kb equals x squared over 0.06666 minus x. What's Kb? You can give it to us. Hey Siri, what's the Ka for nitrous acid?
My web search turned something up for what's the Ka for nitrous acid.
Let's see here. So here's a table. Nitric acid. Oh, thanks, Siri. Oh, there it is. Nitrous acid. 7.2 times 10 to the minus 4. It's the Ka. Ka equals 7.2 times 10 to the minus 4. On an exam, that would be given to you somewhere, either in the problem or on the table of useful information. That's Ka. but this is equal to KB. What does the book give you? 4.6 times 10 to the negative 4. Well, let's go with what the book says. Because this isn't telling me what temperature or anything. Okay, let's go with that. 4.6. KB is KW over KA. KW 10 to the minus 14. KA 4.6 times 10 to the minus 4. X is small. So X equals the square root of 1 times 10 to the minus 14 divided by 4.6 times 10 to the minus 4 times 0.0666. 1.20 times 10 to the minus 6. Anybody else get that? So X is definitely small. What does X equal? COH concentration. So, from that, POH equals 5.9194. pH equals 14 minus that, 8.08. Any questions? Is it reasonable at the equivalence point for the pH to be slightly basic there? Yeah. Because when you're titrating a weak acid, at the equivalence point, what you have is just the conjugate base. And so it will be slightly basic. What if we're titrating a weak base with a strong acid? Very similar. So it's going to start with a high pH, go to a low pH. You're going to use KB for your weak base to find the initial pH. The half equivalence point, the pH will equal I believe that would be the KB. And so up here, you have a buffer going on, and so you can use the pKa of the conjugate acid. Down here, you've got excess hydronium ion. Is this section never going to end? I'm so done with this. Let's just stop here.